consider a certain domain, that would be what you see, the round domain, which contains a substance, a fluid, that can undergo phase transitions. So I will assume that one phase or one fluid, fluid 1, would occupy, for instance, these two components. Could also be more than two components. And then there is an outside component. So I would like to make sure that the components do not touch each other, and there should be no boundary contact. So if you want, so that's like a local representation. And what I have in mind is, again, so two heat conducting fluids, incompressible, viscous, and again the domains. So the quantities that you will see me using is a velocity, the surface velocity, and it will always have a subscript gamma. So it moves, it doesn't have to be like, I don't mean normal velocity or normal direction, it's a velocity. Now, having a fluid, let's say, as it stands right now above or below, or if you go here, inside, outside, these fluids will also have, well, and this is a quantity that I would also need, you would see that a little bit later, normal velocity, so that's a scalar quantity, it just measures the amount in normal direction. So again, we will have to look at differential geometry, so the mean curvature will play a role.
I'm lost. U gamma is the velocity of gamma t.
Yeah.
In the normal direction?
No,
or
no,
a particle, it's the velocity of a particle of gamma t.
Yes.
Okay,
Yes.
so
Yes.
it's particle velocity,
Yes.
and then you project on the normal.
Yes. Yes. But so what you will see is, thanks for asking. So if I have a quantity that is defined like outside, inside, that is continuous up to the boundary, then every so often I will look at the jump. The jump would be like here, outside minus inside. Now comes the issue with the fluid. So each fluid will have, the one in omega 2 will have a velocity, the one in omega 1 will have a velocity. And since we're also considering phase transitions, in general, they will not coincide. So this will become clear a little bit later. So you could think of having, let's say, the outer one ice containing water, and the ice would be flowing, the water would be flowing, and at the same time we allow for phase transitions. Or the other way around, you can have a lake and you can have ice inside the lake. However, it should be submerged, because otherwise you will have like three boundary contacts. So each fluid will have its own density. A little bit later I will take those to be constant. And for the moment, let's just look at the internal energy of each fluids. So they're physically distinguished. They have own energies, own densities. Now, what I would like to show you a little bit is, so what we are looking at is the balance equations, for instance, balance of mass. So this is the well-known part. But let me take you a little bit through this condition here, the jump condition on the moving hypersurface. So that's known to most of you, but let me quickly take the time just to show you where it comes from, because it's an important quantity. And you also see that we have to face the issue that the surface velocity is not necessarily equal to the fluid velocity. So what you see here is really the jump. So this rho, the quantity, would be different, the density, in a region omega 2 from omega 1. The same would be true for this quantity, u. However, u gamma, of course, is only defined on the moving hypersurface. So where does this come from? So you can see it quite easily if you look at the total mass. So we keep in mind we integrate the density all the way up, but we have to pay attention that we are looking at subdomains that have a time dependence, and we are looking at quantities in general. Right now they're time dependent, which might be different. So I cannot ignore the motion here. I have to take it into consideration. So you go through the derivative, and then it's clear if you take the derivative, first you ignore the motion here and just go to the inside function, do the same here. And then the next thing is we could keep in mind that omega 1 is moving in omega 2. So if you do that by the transport theorem, one of the transport theorems, what you're going to see is you will pick up, so rho 1 that stays as it is, but then you will pick up normal velocity. And normal velocity, so the sign of course has to do with the sign convention that I oriented so that the normal points from omega 1 into omega 2. Now, what I will do in the next step is, so you see here there is a normal velocity. What is different is rho 1 density minus rho 2, so I will take them together and this will be a jump quantity. So this is what happened. So this generates a jump. We keep in mind the jump is actually only caused by the different densities here, because again, u gamma doesn't experience a jump because it's defined on gamma of t and the outer normal the same. Then you go in and use now the equation, conservation of mass from the bulk equations. Here you go, and then the next step is of course quite clear. You use the divergence theorem, and again, due to the normalization, this is what comes out. Now I will look at these two quantities, rho 1 u1, rho 2 u2, and I will collect them. So this will generate a jump, and I will take the jump and combine it with the second one. And what you have here is where we started, so the jump condition. So again, we have to keep in mind that the fluid velocities are do not necessarily coincide with the surface velocity, because of a phase transition. Now, so this is a repetition of the basic balance of mass. So we look at the condition and we are going to say, well, if the jump is 0, then I can look at this quantity, let's say in omega 2, and I can look at the quantity in omega 1, so I know it has 0 jump. That means that no matter if I come from the omega 2 side or omega 1 side, this is the same quantity. So it's well defined. So once I have this well-defined quantity, it's a scalar quantity, then this will be called the phase flux. So in a certain sense, it measures, at least in normal direction, how the motion caused or the motion of gamma of t caused by the phase transition differs from what the fluid would do. So well, let's quickly continue. So in case that J does not coincide or is not 0, then we have a phase transition. If you're looking at the case that J, the flux, is 0, then you go back and you're arguing, well, then the left-hand side is 0. So on the right-hand side, potentially you have two equations, one for the 2 part, one for the 1 part. They are the same, so what you can do is you can just divide. Left is 0, you divide by rho 1 or rho 2, and what you get out pretty quickly is that this is correct. So if no phase transition occurs, then what you see is that there is no difference anymore between fluid velocity and the velocity of the moving surface. So we should keep in mind, if you only look at fluids that do not experience a phase transition, then what you always have is gamma of t is just transported with the fluid. It's advected. So wherever wherever the fluid particles take you, that the fluid travels around. So here it's different. And then we also have to, and you will see that will play a role. So it makes a decisive and a huge difference whether or not you have equal densities or different densities. If you have different densities, then there is something that will happen. It's a jump in the normal component, and people know that these are so-called Stefan currents. And you see that it makes a difference that in order to have this quantity, and again, it's the same quantity, no matter if you are in omega 2 or omega 1. So you see, in order to have that, if you have a different rho 2 here from rho 1, then U2 has to be different from U1 too. So that means there is a discrepancy between U2 and U1 There is a jump. So the phase flux will be with us from now on. Now,
can I ask a question?
yeah.
Sorry, this is a silly question, I guess. If I put particles in omega 1, and I put particles in omega 2, and I put particles on gamma, and then at time t equals 0, and then I follow their trajectories through the velocities u1, u2, and u gamma. Does a gap appear?
So it can appear if you have different densities, yeah.
I guess in the case of different, I'm thinking
Yeah,
in terms of
and
different-
also in case of equal densities, yeah.
So what's in the gap?
So if you only had, so you could think that you have right now, if you ignore the motion and you're sitting right here, here is ice, here is water, then it melts and it's gone. So that's the melting gives you an additional component.
It's to do with shrinking of the shrinking.
Yeah, yeah.
So somehow or other there is a vapor phase which is suddenly here.
Yeah.
Which we're ignoring. So we don't have an. So if that happened, there would be no PDE in the gap.
Well, here, I mean, I will just have the two components. Either it's one phase or the other phase. So there is not like something in between that. So what the next thing is, and these are now, of course, the standard balance of momentum. And the only thing that I would like to pay a little bit attention is, you'll rather see me, so this comes out from balance. And if you go back here and take the U and combine it with the parenthesis here, and look here at the tensor, so what you see is what comes out is the J shows up again. So T gamma, that's the bulk stress. T is the bulk, or Ti the bulk stress tensor. That's surface stress. And you will see that the assumption that I will make is that surface stress is generated by or is proportional to the mean curvature vector. So I'm ignoring, for instance, so I do have results for that, but here in this talk, we're ignoring that sigma could be temperature dependent. The thing changes, the thermodynamic changes, I will point that out. So I'm ignoring the effect of Maragoni forces, or you could also have surface viscosities, which makes it even more complicated. Now, one more balance equation, balance of energy. And you will see that the energy that we're dealing here would be kinetic energy, and then you have internal energy, and you have an energy contribution coming from the surface. So it plays, well, so in a next step, we are looking at making it thermodynamically consistent. So the temperature should be read as absolute temperature. Then I will assume so the temperature will be continuous, so there will be no jump for the temperature across, let's say, across gamma of T. And then this would be a constitutive assumption. So each fluid will have a Helmholtz free energy. So physics would tell you what's for each fluid what's reasonable. So once you have the free energy, then this comes from thermodynamics. So you have an internal energy. The internal energy being the sum of the free energy, and one component coming from entropy. So probably the physicists would say that with this part, you're not generating anything, it just generates heat. And with this part, you can do work. So if you have entropy, and out of this comes heat capacity. So everything goes right back to the free energy. So that's one way of taking the temperature as a free variable and then expressing the energy and all the other quantities. And then there's latent heat. So I will assume that the heat capacity is strictly positive. And this is also more or less a constitutive assumption that there is one number, exactly one, where the jump of the free energy is 0, the melting temperature. So I think people have told me that if you look at certain polymers, it can happen that you don't have just one sharp value where melting occurs, but it can happen on a whole interval. And then you will also see that later I will not bother using the index I anymore, but you should keep in mind that all the quantities can be different or will be different in different phases. So for instance, also the density for water and ice, for instance. So once I have
So since this is compressible mechanics, right?
incompressible.
Incompressible.
Incompressible, yeah.
Okay, so you are assuming some. Can you assume some simple assumptions on the entropy?
So what you can do is you can go back and, for instance, ask what would it mean to have heat capacity that is constant? What would it mean to have heat capacity that is constant but different? And then you can go back, and from this equation you would see, for instance, what the free energy is. So you would end up with something like, in that one case, temperature times a logarithm, what you usually see.
You can assume in some simple case, all of this is functions of theta that are known.
Yeah. Well, this one is known, and then the rest is given.
And what is the typical shape? Psi I of theta.
Again, it could be something like a theta times logarithm theta.
Which looks like the Boltzmann entropy.
Yeah. Yes. Yeah.
Okay.
Excuse me, there's something that's bothering me.
Yeah. Sure.
The velocity of the interface. Where do you get this number?
So it comes.
Because I don't see that you will get it from some equation.
Well,
But
you
up to now is
let me
data,
maybe
and
let
it's
me
not
maybe
data.
give you at in
the
5
end,
minutes I will come
so
back to
at
you.
the end you get
Yeah. I will show you the equation, and then I will specifically ask you if I answered the question, if you allow me. So out of once you have entropy or specific entropy, you have total entropy, and again we want to be careful because these are different quantities, and I should have mentioned rho now is constant, rho 1 is constant, rho 2 is constant. So this is something that we put into the modeling approach, and that is the only way entropy is produced is through friction in the bulk phases. So I can also handle the case where there is entropy production of gamma of t, and this would, for instance, occur if you have surface tension that depends on temperature. Then this becomes also free energy, and then you also have surface entropy, and we also have thermodynamics on the surface. So if you go back and start taking the derivatives, again you would have to, because of the jump, you would have a transport theorem, you would involve all the laws that we have already listed, and what you see is that the derivative of the total entropy is this quantity, and this, so T is a matrix, this is a matrix. What this means is you look at the one is symmetric, so you look at the trace of this matrix. So that's a scalar quantity, that's a scalar quantity, that's positive being absolute temperature, but you also pick up this contribution, and this bracket here would not have a sign, so you don't know if it's positive, negative. So what you want to do is you want to insist that this quantity is 0. So if you don't want, so if you want to have like the derivative of the total entropy to be non-negative, we insist that this is 0. And this becomes like a constitutive assumption. And what you see in here is for the specialists, that's actually the Stefan condition. So here the Stefan condition comes in, not what probably you have seen more often through an energy consideration. It comes in from the requirement that there is no entropy production. So this will be with us as a condition. This quantity should be 0, and I would have to tell you what's Q. Q is the heat flux, and Q a little bit later I will make Q being, or I will ask, that is proportional to the gradient of theta or to negative, and then you see that the sign will be positive, and you will see something good coming out. So these are the things that well, let me just we can take you through it. So on the fixed boundary, there is no flux out of here. We will insist that there is, so the fluid is sticking to the outer boundary, and then we're just looking at it. So this is an Newtonian fluid. This is the stress tensor, deformation tensor, and again the heat flux, so each fluid has a known heat flux, is proportional to the gradient. And with the usual physical quantities. Two more things that I have to tell you, and then I'm ready to tell you what you end up in terms of PDEs. So here I'm repeating, that's a short way of saying that theta, the temperature, does not experience a jump. So I already had this. This one is saying, so I want that P gamma, what it does is, if you're sitting on gamma of T, it looks at the projection onto the tangent space. So if you look at U1 and U2, and you look at the tangential components, outside, inside of the fluid motion, then they agree, so they have the same value, and they coincide with the tangential component of the fluid motion. So tangentially, there is no discrepancy between the fluid motion, the U1 and U2. This is the condition that we saw before. Again, has to do with entropy production. And let me quickly convince you, if you put that in and you go back, and here I'm repeating what I had for the derivative of the total entropy. So this is gone, and you substitute in your assumption for the heat flux, and you see this is what comes out. And what you see is, so the only way to generate, or the way to generate entropy is by if you want, by friction, coming from here and coming from here.
But why, for instance, why you could ask that the integral is zero instead of transfer?
Yeah. But then this is a condition that you would see anyway. It comes up in fact in phase transitions in any case. And you would see a little bit later. Actually, I need the stronger conditions. Yeah. Okay. So this is a repetition. And now the only condition that I have to spend a little bit some time is, this is the last condition that closes the system, and it's also possibly the most difficult condition to understand, and that's also the one that you would not necessarily
Could you write
find.
for us the expression for J? So
Yeah.
we will make sure.
So J comes out from, so I'm looking at rho, and I'm looking at U minus U gamma. So these are vectors, and I'm taking the scalar product, and then I'm taking the jump.
So it is the mass flux.
Yes, yeah. So what comes out is, so if you now use this principle, so you want the energy balance across the interface, you want this condition, then at the end, by taking derivatives, this is a quantity that shows up in an integral, and this now has to do with conservation of energy. You want to insist that it is zero, then you're going to say, well, J at the beginning has to be or is considered an independent quantity, and you end up that everything that is in the bracket here has to be zero. So I will show you a little bit later that if I ignore fluid motion and then would have the Stefan problem, then I will convince you that this in here is actually what you know as the Gibbs-Thompson for the Stefan problem. So it's more complicated. So in this approach, it comes out from these principles. You would find in the literature, or we are aware of one source where exactly this condition is derived. That's in a paper, I will show you that later, by Anderson Gertin. They're using the principle of configuration forces, ending up with the same condition here. So what do we get now? So if you collect everything, all the principles, then this one would be that's what happens with the fluid. So in here you have Navier-Stokes, incompressible Navier-Stokes, incompressibility, stick condition. This one is a convenient way of just saying U doesn't experience a jump in tangential direction. So you see what's going to happen in normal direction. You can have a jump, and you also clearly see if there is no phase transition, then the right-hand side vanishes, then U doesn't experience a jump. Or if you take rho to be rho 1 is the same as rho 2, you can also look at 1 over rho and take the jump, then it's also 0. Also in that case, you would not experience a jump condition here. So this is a condition coming in that has to do with, again, conservation of momentum on gamma of t for Navier-Stokes. So more or less what you have here is Navier-Stokes with a free boundary with the complication that there is a J here, there are phase transitions. Now you go into conservation of energy, and I will also try to convince you a little bit later. This is more or less what you expect from a Stefan problem. If you take U to be 0, then this would also vanish. So this is conservation of energy. That is something that I insist on, so it's no flux across omega of t. This is something that again we insist from the beginning, it's continuous. And here that's again the condition, Stefan condition, of the condition asking that there is no entropy condition. Now there is one, if you count the conditions, you would know there is one missing, so this one closes the system. And now this is the law that describes the motion of gamma of t. And I hope, Naomi, that this is what you asked for. So you have a quantity here, then you have, what does it tell us again? It tells us that the surface is not just transported with u, but it also moves according if there is a phase, if there is a flux here. So mathematically, what would you do? So the approach is that you do the transformation to a fixed domain, you parameterize in normal direction. And if you do that, if you parameterize in normal direction, then what you pick up here is a time derivative of a height function plus a scaling factor. So here you see like the derivative of a height function. U is given anyway, it's a system variable. And J, you have various ways to express J. Either you can go back and solve this part for J and put it back in here, or possibly through here. So you see that the variables right now, U is certainly a variable, pressure, temperature, and gamma again is taken care by a height function measuring it. So there is a PDE in here, time derivative, and hidden in here, time derivative of a height function. And then you have a set of PDEs that of course couple. So you see the coupling, there is, although it doesn't show up here, but this is temperature dependent. Then you see there is coupling obviously here from the fluid motion, there is coupling here. Now, what I will do from now on is I will look at the simpler case where rho 1 happens to be rho 2. And you will see, and I will highlight that a little bit later, that there will be a simplification here. If you have the same value, and even if you look at 1 over the same value, so it would be like 1 over rho minus 1 over rho, well that's 0, so this would vanish. I will show you that this would vanish, and it gives you a simpler system. The interesting case here is, and that gives mathematically, it's actually very interesting, you can look at this system and look at the boundary conditions. Here, for an analysis, it pays off if you take the projection to the tangent space. So this would leave you, if you look at the projection, with n minus 1 equations for u. And I would take the remaining one as a definition for j and plug it in here. Then you can look at, just count the conditions on the stress, or the normal stress. You would have n conditions here and 1 here. So if you're more familiar like with, let's say, Stokes, if you make it linear Stokes problem, Stokes equations, there is as soon as you have different densities, it generates an asymmetry. It makes it mathematically a very interesting problem that has not necessarily, or we are not aware that people have looked at it in the literature. So be it either if you forget about time dependence, if you forget about the nonlinearity and look at the Stokes, we call it the asymmetric Stokes problem. Now, and of course, the initial values. So the work that I mentioned is, so you would find this, what we call the generalized Gibbs-Thompson in a paper from 2007, coming from very different principles. The idea of looking at conduction-convection problems has been done before, but these are simpler settings, so no mean curvature. One of the phases resting, weak solutions. So what it was here with my colleague Manuela Di Benedetto was basic, like one of the issues show that the regions are open if you look at the weak formulation. Now, yeah, so what I would like to not convince you but mention is, of course, so this is something that we put into the model, of course. So it's the total energy is conserved, the total entropy is non-negative, or if you change the sign, it gives you strict Lyapunov function. I'll quickly take you through that because it's instructive how to get there. Now, I will also convince you that you know if there are no external forces, then we know all the equilibria. And you will see, I will convince you about that. The equilibria have to do zero velocity, constant temperature, constant pressure. And if it comes to the geometry, then what you would see is if you have two boundary components, like the dispersive phase has two connected components, then you would have that this has to be a sphere, and this has to be a sphere, and they need to have the same radius. So the interesting question later, so if you have an equilibrium situation with one sphere here, another one here, or ball, or let's call it ball or sphere, they need to have the same radius. And a little bit later, I would also like to convince you about stability. And you will see there is a connection with thermodynamics. If you have like two balls, can they ever be stable or not? You will see that thermodynamics will tell us a thing or two about it. So you can count how many, or you can look at the dimension of the equilibria. And what you would see is, so the mn plus 1 come in from geometrical considerations. If you have one sphere, you can take the sphere on a given energy level and move it to wherever you want. You will not change the energy. So if you take your favorite sphere and move it like one direction, two directions, three directions, gives you three degree of freedom, then you can take it and make it bigger. If you have two spheres, you can move them independently, but you cannot only make them bigger or smaller by having the same radius. There's again a little discrepancy, so the dimension increases if you have different. This has to do, well, maybe I'll come back. This has to do that there are two here with different densities. There are two quantities that are conserved, energy and phase volume. Here only energy. Let me quickly show you about, because you will quickly see how this goes. So if we assume that entropy is constant on an interval, take the derivative, this is the formula that we have. So if this is 0, then it certainly forces the gradient of theta to be 0. This means that it forces theta to be constant here, constant here, but theta was assumed to be continuous, so you see that theta has to be just one constant. Coming out, gradient is 0, constant. So if it is constant, then you go through this equation, you take a derivative, and then you decide that J has to be 0 under the assumption that latent heat is not 0. So good, so temperature is constant. Now also this quantity has to be 0, and here that's the deformation tensor. So you go through it. So So the deformation tensor is 0. You go back, J is 0, then there is no jump here. U doesn't experience a jump. Korn's inequality tells you that the gradient is 0. Since it's 0 outside, it has to be 0, constant 0. So if the entropy is constant, we see that we're already at an equilibrium. That tells us that it's a strict Lyapunov function. So there are 2 more or 3 more equations that we haven't used, and it's hidden a little bit in here. So if you go from left to right, so U is 0, that makes this quantity 0, but we have to keep in mind that T contains, well, it's deformation tensor, and there is also a pressure gradient. So since this is 0 and the right hand side is 0 anyway, the pressure gradient is 0. That would mean that the pressure is constant in omega 2, then it's constant on this component of connectedness and also on that one. But a priori you can have, in this constellation, you could have 3 different constants. But then you go in and say, oops, then you go in and say that, okay, here we go. Look at this equation here. You're going to say, well, J is 0, so this vanishes, the velocity vanishes, and there is one condition that sits in here and says also this jump is constant. Then you go back and say theta was constant, so it means that what comes out is you can only have, so in omega 2 you can have a constant, but it's the same constant in omega 1 in this component than the other one. This has to do this condition. Then you go back to the last equation, where are we? To this one with the mean curvature, and here is also here is a jump of the pressure, it's written right here, and you're deciding, no matter whether you're sitting on this part of the free boundary or on this part of the free boundary, it's the same constant. So you're saying mean curvature is constant, it's embedded, that means you have a sphere here, you have a sphere here, and it's the same number here, so they have the same radius. So this gives us what the equilibria are. Now comes the simplification. So if you take again rho to be rho 1 to be rho 2, then this box will vanish, this box will vanish, and this box will vanish. So they will be gone. Then what I see me using is, since this is gone, I will take part of this equation and take the dot product with nu gamma on the right hand side, and this would just give me mean curvature times sigma. I will take that and go down here and say, since rho is constant, I can pull it out, and then you're gonna see here, since nu gamma does not experience a jump, I can move it in and out, it doesn't matter. So I can go back, and what I do here is I substitute in mean curvature. So you will see this will be changed, this will be changed, this will be gone, and here you will see something, not the stress tensor anymore, but rather just mean curvature. And so this is now the set of equations in case of equal densities. And let me just for 1 minute take you through. So what would happen if you don't have fluid motion? The Stefan problem. So if U is 0, then there is nothing coming from here. And what you end up here is where you would have a time derivative in theta, you would have this condition, you would have this condition, you would have this condition here. And if you look a little bit, and then what I will do is, one will be redundant. I will take and replace the flux from here down here. And what you see is, so this is the Stefan problem, and you have a thermodynamical consistent formulation of the Stefan problem. And you can also analyze, well, it's a special case of what we already did, so you can also analyze what are the equilibria, and they are the same. So this is too technical.
So what is the the practical form of the Gibbs-Thompson law? Could you show the slide again?
So what you so this is maybe if so in the literature, since the thermodynamic consistent Stefan problem has not been considered, you should read that as, so if you look at, thanks for the question. So we know that C of melting temperature is 0.
Yeah.
So what you can do is you can basically just linearize it, tailor expand it around this value,
Okay.
and what phi of E would become, have something like this, and then you have, well, um of course, then you have U minus um, so this would be now melting temperature, this would be relative temperature, so I express everything by relative temperature, and what you then have is,
But why are you allowed to take as UM as the base temperature? I don't see how you center about the melting. The melting temperature plays an important role in the formulation. For example, the melting temperature.
so
How
probably,
do you make it coincide, the melting temperature with the free boundary?
so just let me just back step and then I try to answer.
Example.
So if you go to the literature and look at the Stefan problem, then
Yeah.
probably the fairest way would be that what you see in the literature is close to melting temperature. So that's and that comes out as a first approximation here.
So, okay. And in this case, the melting temperature does not enter in the formulation because it's hidden in the psi.
Yes. So what you do is, if you want to do that, then you just go through the oh, I'm sorry. So
Yeah, but this is an important question.
so I should you know
Then you
what
can
happened
have-
is I have to call
You can
this.
have phase transitions away from the melting temperature.
Yeah. Let me just, it has to be theta. So the temperature used to be, in my younger life, used to be U, but not anymore. So I have to
Yeah.
put it theta. And then what you do is you just look at that and maybe call it a different theta,
Yeah.
and then you go back and replace the whole thing in the. So you go back and replace theta by relative temperature here.
So again, the question is, in this model as it is possible to have a phase transition away from the melting temperature. And this is something that is acceptable.
So if just in terms, so this would be solvability, and maybe I will just be a little bit faster here. I mean, and you would see with some amount of initial regularity for the temperature, for the velocity, for the geometry, I guarantee you in some, these are compatibility conditions, I guarantee you local existence, and the remaining of the talk, I would rather like to spend a little bit about what does thermodynamics do for us for the equilibrium. So the right way to look at the equilibrium is you're gonna say you have a certain energy level, and you're gonna ask on that energy level, where are the equilibrium? So if you fix the energy level, then the equilibrium will be exactly the critical points of the entropy with the constraint of prescribed energy. So the thermodynamics of the entropy tells you where the equilibria are. Now you look at the entropy functional, and you look at what can you say about local maxima and local minima, and what you will get out is, so at the end of the day, if you want to have equilibria which are at equilibrium, thermodynamical equilibrium, then you have to expect that if you have a stable equilibrium, then if you change it a little bit, you have to expect that if it's stable, then it will relax. That means by changing it, there's no way that you could produce entropy, otherwise it would run away. So that means you're already at a local maximum of the entropy for the stable equilibria. And here you have, well, you have kind of mathematically precise. So if it is not connected, you will not have a local maximum. If it is connected, well, necessary for the local maximum is that it is connected. So what I will convince you a little bit later is this has to do that if you have more than one equilibrium, it cannot be stable. So this has to do with maybe a little bit like onset of ripening, or Oswald ripening. So the last thing is maybe so. So I can do a linear analysis of an eigenvalue problem. It's a complicated eigenvalue problem because it couples. This would be a Stokes problem. This is a elliptic transmission problem. It couples through this equation. Lambda shows up here, it shows up here, it shows up here. So if you want to say something about the eigenvalues, you need a very precise, detailed analysis of this problem. For instance, what you're going to do is you could say you solve this problem for u for given h. If you have u, you take that result, the output, and put in here, then it's a function of h alone. Then you solve the transmission problem and put it in here. So you can reduce it to an equation of h alone, and then you try to analyze, can you say about the eigenvalues, and this is what comes out. So it's the multiplicity is consistent with the dimension of the.
Okay, try to follow. Could you go back? Where is this Stefan condition?
So what happened before? We had a time derivative here.
Yeah. So you
Before
don't
we
need
had
it anymore.
Yes, so we had a time derivative here from Stefan.
Oh,
And if you want, so this has to do like the one way to read the Stefan condition and substituting in. So this is what you would see if you.
and you eliminate the transport term with the first equation.
Yeah,
You
yeah,
use
yes,
Stokes.
it's the linearization. That's right. So these are the nonlinear terms. Quadratic. So if you were just looking at the Stefan problem, then you would have this simpler sub-problem where u doesn't show up. If you only do Navier-Stokes, then you have something similar.
Yeah,
and-
it's
and
not a
so
simple
this
one.
one is
Yeah,
simply
yeah.
more complicated. So what you will find out is, so there is the dimensions are. So it has the same dimension as the dimension of the manifold. You can show it semi-simple. And here's the interesting case. So there is a quantity that tells you the following. If you take m to be 1, then we are looking exactly at one sphere here. So if m is 1, then you have to make a decision. Either this quantity is negative or it's positive. If you're in this case, then you have no positive eigenvalues. If you're in the opposite case and you just have one sphere, you pick up one positive. So that means for one single sphere, there is a regime where a single sphere is stable, and there is a regime where it's unstable. This also has to do, you recover the same quantity if you go back and ask what makes the critical point the maximum for, or the local maximum for the entropy function. If you have two components, then in any case, no matter what this quantity tells you, you will also always have positive eigenvalues. So, and this is something coming out of the theory of dynamical systems. You show it's normally stable, it's normally hyperbolic, and what comes out is at the end from the eigenvalue consideration, you're deciding that a single sphere is stable in this case, and it's nonlinearly stable, it exists. It exists globally, converges exponentially, and if it is connected, and this is the case, then certainly it's unstable, and if you have several, then it's also unstable. So this constellation would always lead you to an unstable configuration. So this stings If you change it a little bit, they will start moving around. One might get bigger, one might get smaller. So what else? So maybe I will probably not show that. So we also have some what a priori estimates do you need to make sure that you have global existence, and I would say, if you know that the components cannot touch each other, cannot shrink, cannot go to the boundary, and you have some a priori estimates, then you would also find out that you have global existence. So maybe as a summary, there is a very interesting connection again between the position of the equilibria and the entropy functional. The entropy functional, the fact whether you are at a local maximum or local maximum of the entropy functional tells you something about stability, and at the end you can prove it mathematically that what the entropy functional hints you that this happens also mathematically. So I think this might be a good time to stop now.
Questions? Comments?
So I have to come back to, I didn't give you a good answer. A good answer for the question whether phase transitions can also happen away from equilibrium. This was not a good answer. So you were right. Yeah.
Now, so the stability is based on the analysis of this eigenvalue problem.
Yes.
And can you show? I mean, I don't see how the energy plays a role. Could you repeat it a bit? When you get this eigenvalue problem,
Then it's gone. So the energy, where I mentioned energy had to do that you ask the question on a given energy level, what are the equilibria?
yeah,
And you answer it on a given energy level. You have to look at the critical points of the energy functional. And as soon as you have the critical points of the energy functional, you know these are the equilibria. And not the energy, the entropy functional.
yeah.
And so there is a one-to-one correspondence. Once you say that, then you forget about energy, and well, no, it's still there. I mean, you still have the constraint, and then you check what about are the critical points minima or maxima, not minima, or
For the energy.
yeah, for the
You
entropy.
get the critical points for the entropy, and then you go to the energy to see if they are maximum.
No, it's on entropy with the constraint that energy is. And once you know what they are and do the analysis of the eigenvalue problem, then it's a coupled set of like a Stokes problem, a transmission problem, plus an additional coupling.
Anything else? Let's stand the speaker again.
Thank you.